Today we will be answering the questions: what is moment of inertia? What does it represent? And how do we calculate it? We can define it as the distribution of mass around an axis of rotation. The definition of moment of inertia may seem abstract at first. We will show how to compute this value mathematically, but first let's approach it with a practical definition. You may recall that for many of the formulas in rotational motion, we have analogous linear motion equations. Some examples that include moment of inertia, represented with a capital I, include Newton's second law, kinetic energy, and angular momentum. With the linear counterparts, we can see that the moment of inertia is a direct rotational analog to mass. Let's focus on Newton's second law to see what this means. In the linear form of Newton's second law, a net force gives rise to an acceleration. The acceleration is inversely proportional to the mass, which means that the more mass the object has, the harder it is to accelerate. In the rotational form of Newton's second law, a net torque gives rise to an angular acceleration. This angular acceleration is inversely proportional to the moment of inertia, which means that the larger the moment of inertia is, the harder it is to angularly accelerate. So what does the moment of inertia really mean? What does it represent? Here are 3 examples to help us understand what the moment of inertia means. Imagine standing straight up, holding a dumbbell in each hand close to your chest. If you try turning from side to side, it's not much more difficult than doing it without the weights. However, if you try to extend your arms and perform the same motion, you will find it requires considerably more effort, even though the total amount of mass is still the same. The reason for this is that, even though the amount of mass is the same, it is distributed differently. The mass of yourself, plus the dumbbells, is now, overall, farther away from the axis of rotation, which means that the moment of inertia has increased, so more torque is required to rotate. Another example is when we roll differently shaped objects down an incline. Let's say that we had a cylinder, a hoop, as well as a sphere, all with the same mass and radius. If we allow them to simultaneously roll down an incline, we'll see that they roll at different speeds entirely. The reason is that, even though they have the same mass and the same radii, the way their masses are distributed is different. The hoop has all of its mass distributed away from the axis of rotation, giving it a higher moment of inertia. Therefore, it is slower to accelerate. Similarly, the sphere's mass is overall closer to the axis of rotation, so it has a lower moment of inertia and is therefore the quickest to accelerate of the 3. Finally, let's take the example of a rotating bar in a couple of different ways. First, we hold it by the center and spin it back and forth. Now, hold it by the end and try the same motion. You'll find that it takes considerably more effort. If we instead were to roll it between our hands along its long axis, it is very easy. We rotated the same object 3 ways, but we notice that the moment of inertia is quite different depending on the chosen axis of rotation. In the first case, the mass is overall somewhat close to the axis. In the second, the mass is overall as far away from the axis as we can get while still holding the bar, so the moment of inertia is higher. In the third, the mass is all very close to the axis, drastically lowering the moment of inertia. Now that we understand the idea of the moment of inertia, let's look at how to actually compute it. First, we start with the moment of inertia of an individual particle. The mathematical definition is the mass times the square of the radius. This radius is the direct distance from the axis of rotation to the particle. So, the heavier the particle is, or the farther away from the axis it is, the harder it will be to rotate around that axis. If there are multiple particles rotating around the same axis, then we simply add their individual moments of inertia to get the total moment of inertia. How about finding the moment of inertia of objects we can't treat as particles? Depending on the level of physics you're taking, the formulas will either be provided to you, or you'll be expected to derive the formulas yourself using calculus. A video on the calculus derivations will be linked in the description below. Here are some common moment of inertia formulas. Take note of how each formula includes the mass of the object as well as either a radius or length. The key difference between them is their numerical coefficients. This number can be thought of as a sort of distribution factor, representing how far the mass is spread from the axis of rotation. It's determined by the shape of the object. The rotating sphere has a relatively low factor because much of its mass is near the axis of rotation. The rotating hoop has a higher factor of 1 because none of its mass is near the axis of rotation. Now, take note of the rod rotating about its center versus the rod rotating about its end. Even with two identical rods, rotating about the ends will have 4 times the moment of inertia as rotating about the center, as the mass is farther away from the axis on average. This agrees with the assessment we made in the third practical example. More information on why these two moments of inertia are different will be covered in our video on the parallel axis theorem. Finally, we may ask, what if there are multiple objects rotating together? As was the case with particles, we obtain the total moment of inertia of a compound system by simply adding together the individual moments of inertia of the constituent objects. Note that the objects must share the same axis of rotation. If an object is offset from the axis, we must find its proper moment of inertia using the parallel axis theorem. In conclusion, we can think of an object's moment of inertia as a measure of how difficult it is to change the object's rotational velocity. It's determined by the object's mass and size, but also it depends on how exactly that mass is distributed. The farther away the mass is from the axis, the higher the moment of inertia is. Understanding these ideas will help us fully grasp the role that the moment of inertia plays in all of its applications, such as Newton's second law, rotational kinetic energy, angular momentum, and more.